morning all. This is the second session of the webinar series by Postgraduate Department of Mathematics and IQAC of K.K.T.M Government College, Pullut. Now I invite Srimati Srija K.U, Assistant Professor, Department of Mathematics, to deliver welcome speech.
A very good morning to all. I am very happy to welcome you to the second webinar organized by the Postgraduate Department of Mathematics and IQAC of K.K.T.M Government College, Pullut. First of all, I welcome our principal, Dr. Nessie E. She is very supportive and always with us with her suggestions and guidance. Welcome, ma'am. Our first webinar was greatly appreciated by all the participants. So today we have the second one on the topic, an introduction to Cech-Closure spaces by Mr. Yogesh Prasad. Sir started his teaching career at PG Department of Mathematics, KA College, K.T.M. Then he worked as Assistant Professor at Rajgiri School of Engineering and Technology, Cochin. Currently, he is working as Assistant Professor at Department of Mathematics, Bishop Moore College, Mavelikara. He is doing his research at IQAC, and his areas of interest are lattice theory and topology. It is my great pleasure to welcome my former colleague and friend, Yogesh, to this webinar as a resource person. Welcome, sir.
Thank you so much, Srija.
Okay, thank you. Our IQAC coordinator, Dr. Sindhu SL, is actively involved in academic activities to the session. I also welcome our dear HOD, Sadi teacher, for her continuous support. Otherwise, it is not possible to conduct a webinar like this. Welcome, teacher. Finally, all the participants, including my colleagues, a hearty welcome to this program. I would like to appreciate your interest in exploring the opportunities like this in this pandemic period. I hope this will be a fruitful session for you. Once again, welcome you. Thank you. Now I invite today's speaker, Yogesh sir, for this presentation.
So thank you so much, Srija Miss, and the organizers for introducing me for this lecture. And good morning, all. Now, I share my slides here. And I hope that most of the participants are PG students, and all are aware of what is topological spaces and what is meant by closure, and what is continuity, homeomorphism, and all basics of topology, at least topology 1. I think everyone knows all these things. And my topic also very much similar to topological spaces and all these concepts. Okay. Now, the title of the talk is I think the title of the talk is Introduction to Cech-Closure Spaces. So this is a very introduction. The title says it is very introductory level lecture. I'm just talking on what is Cech-Closure space means, and we are discussing some basic examples of Cech-Closure spaces and basic properties of Cech-Closure spaces, etc., etc. Now look at the title. It consists of 3 words here. So number 1, check. The second word is closure, and third word is space. And I hope that everybody knows all these 3 words very well. So number 1 is Cech. Cech. I think you know Cech, and he was a mathematician and a topologist, a Czech mathematician and a topologist, and known for Cech compactification theorem. I think at least MSc second year students know what is Cech compactification theorem, and also he is known for Tikhonov theorem, the proof of Tikhonov theorem, Cech homology, etc. Again, closure in the very simple language, what is meant by closure means, suppose we have a topological space, and any subset of the topological space will generate a closed subset. That closed subsets are called the closure of the set, and we will discuss it later. The correct definition and all things are discussed later. Again, a space means, in mathematics, a space means a set together with some structure, and we call it as a space. For example, so when we're discussing metric, or when we're studying metric spaces, you know, there is a set X, and the structure is nothing but the metric, the function D, the metric function D, and which satisfying some properties. Similarly, for a normed space, we have a set X, and together with a norm function and which satisfying some properties. Okay. Okay, now, so these are the topic what we are going to discuss. So I start from topological closure operators, and from topological closure operator, we define what is Cech-Closure operator and then Cech-Closure spaces, and what is the underlying topology. There exists a topology. There exists an underlying topology for each Cech-Closure space, and we discuss what is the underlying topology of Cech-Closure spaces. Again, we discuss maps. Maps means some continuous, what is continuity in Cech-Closure, continuous maps in Cech-Closure spaces, homeomorphism in Cech-Closure spaces. And if time remains, we discuss some lattice structure of Cech-Closure operators on a fixed set. Okay. So now move on to the first discussion. We start from topological closure operators. Okay. So I start from the definition of topological space. Suppose let capital X be a set and tau be a family of subsets of X, and we call tau is a topology on X if the first condition X comma phi belonging to tau, if U comma V belonging to tau implies U intersection V belonging to tau, and if UI belonging to tau, which implies union with respect to I UI belonging to tau. That means we have a set X. The structure is nothing but tau is a structure. That means the family of subsets of X, and that family will satisfy some conditions. Number one is X and phi are members of that family. And again, that family is closed under finite intersection, and the family is closed under arbitrary union. Now, the elements of this tau, then we call the pair X comma tau. That means a set together with the corresponding family tau, that structure tau, we call it as a topological space, and the members of tau are called open sets. That means for a topological space, open sets means the members of the topological space are called open sets in a topological space. Okay, I think these are very familiar to each and everyone. Now, in a topological space, open sets are the primitive notion. So what he meant by the primitive notion means, or what is the meaning of primitive notion, and or what is the meaning of primitive notion? So that means, suppose we have a topological space. So in topological spaces, we study different concepts like convergence, continuity, and all these things are discussed in terms of open sets. For example, suppose when you study convergence in a topological space, suppose we have X tau be a topological space, and suppose we have a sequence Xn, when you say that the sequence is converging to a particular point X naught. So what is the definition? What is the concept of convergence in a topological space? So that means we consider any open set centered at the point X naught. We can say that at a particular stage or a particular level, every term of the sequence will lying in that open sets. So that is a definition of convergence in topological spaces. For example, suppose we consider, I said, suppose we have a set capital X, and suppose my topology is indiscrete topology. I think everyone know what is indiscrete topology. So indiscrete topology means the open sets are, what are the open sets in an indiscrete topology? The full set capital X and the empty set phi. These are the only open sets in an indiscrete space. Okay. Now, so I have a sequence Xn. Suppose we have a sequence Xn, and I said that every sequence, or I said that the sequence Xn will converge into every point of the sequence. What does it mean? So what is the meaning of every sequence? Suppose we have an indiscrete space, every sequence will converge into every point. What does it mean? Suppose we take a sequence Xn, and suppose I consider a point, say some X naught, be any point in capital X. Now, the definition of convergence means that we consider any open set centered at X naught. So here only open set are capital and X and capital phi. So the only open set containing X naught is capital X. Okay, so that means in X, every term of the sequence is lying in the set in that capital X. Therefore, we can say that the sequence is converging to X naught. Similarly, you take another point, say some X1, and the open set containing X1 is capital X only. so that we can say that the sequence will converging to x1. Similarly, at any point, you take any point of capital X, so we can say that the convergence, the sequence is converging to that point. That means depending on the topology or depending on open set, here we define the concept of convergence. Okay, I think these are very much familiar to each and everyone. Okay, now, so that is the meaning of what is a primitive notion. Similarly, when you're considering continuity in topological spaces, so as in a topological space, a function is continuous means the inverse image of open set is something. Suppose we have two topological spaces, say some x to 1 and y to 2. F is a function from x to y, and we say that the function is continuous. It means that the inverse image of every tau2 open set is a tau1 open set, and so on. Okay, that means every concept in topological spaces are defined or explained in terms of open sets. So that's why we can say that open sets are the primitive notion in topological spaces. Okay. Now, again, a subset A of X is said to be closed in a topological space. It means its complement X minus A is open. Okay, that is the meaning of closed set in a topological space. Okay. Now, I have two sentences here. So you have to check the truth value of these statements. The first statement is that in a topological space, a set is closed if and only if it is not open. That is the first statement. And the second statement is in a topological space, a set is open if and only if if and only if its complement is closed. So can you say the truth value of these two statements, PG students at least? So any problem in the slides? Someone says I am finding only first slide.
No problem, sir.
Okay, fine. Now, can you check the truth value of these two statements, right, in a topological space? These are the very basic concepts. That's why very simple and very basic things. The first one, in a topological space, a set is closed if and only if it is not open. Is it true? So this is a biconditional statement. That means if you can. That means I suppose I said that a set is closed. So can you give a closed set and prove it is not open? To prove this result, again conversely, you take a not open set and prove it is closed. So that is way we can prove this result. So what about the truth value of the first statement? Is it true or false? Number one is Amal Shaji is. Number one is false and number two is true. And why first one is false? Can you give an example for the first one? Suppose I take x is equal to. So for a simple example, I take capital X is equal to set A comma B comma C, and I define a topology tau is equal to x phi singleton A. So then you can check this is a topology. This tau is a topology. Tau is equal to x phi singleton A, and that is nothing but the Sierpinski space. And now I consider here the only open sets are x phi and singleton A are the open sets. Now what are the closed sets here? You take the complement. So we get x complement is phi and phi complement is x and singleton A complement is equal to set B comma C. So that means the closed sets here are x phi and B comma set B comma C. So the open sets are x phi singleton A and the closed sets are x phi set B comma C. Now I take capital X. Now x is closed. It doesn't mean that x is not open. So here it says that in a topological state, a set is closed if and only if it is not open. So I take X is a closed set. Then its complement. Then it is. We cannot say that it is not open. That means X is also open here. So that the first implication is wrong. Similarly, so I take set B comma C. Sorry, I take set B. Say again set singleton set B. So which is not open because it is not a member of the topology. Therefore, it is not open. But set B does not belonging to the closed set, therefore it is not closed also. That means not open doesn't mean that not closed. Okay, but whereas the second statement is a true statement, that is in a topological space, a set is open if and only if its complement is closed. Okay, right. Thus, suppose we have a topological space, so it is possible to find these four types of sets in a topological space. Number one, open sets. That means they are the members of the topology tau. Second one, closed sets. That means they are complements of open sets. The third one is the third category is clopen set. That means the sets which are both open and closed. Such type of sets are called clopen sets. For example, in the above topology, so I consider X, take X is a both open and closed. Therefore, we can say that X is a clopen set. Similarly, phi is both open and closed. Therefore, phi is called clopen sets. Again, we can find another type of sets called neither open. That means not open and not closed. Randumallata settugal. That is neither open nor closed set. So these four types of sets can be identified, possible to identify in a topological space. Okay. Now, the following theorem. So this is the next theorem. The following theorem gives properties of closed sets in a topological space. Okay. I'm not giving the proof of the theorem. These are all under very simple facts. Okay. Now, this is a theorem. Let capital C be the family of closed sets in a topological space X tau, then C has the following properties. Number one, both X and phi are closed. That means X comma phi belonging to C. Number two, C is closed under arbitrary intersection. Now third one, C is closed under finite union. And conversely, suppose we have a set capital X and the family C of its subsets which satisfies the above properties. That means suppose we have a subset, suppose we have a set capital X and suppose we given a family of subsets which satisfies these three conditions, X phi belonging to that set, and it is closed under arbitrary intersection and closed under finite union, then it is possible to find a unique topology tau on X such that capital C coincide with the family of closed subsets of X tau. So what is the meaning of that theorem? That means suppose we define topology using open sets. And here we can say that suppose we have a collection of sets and another collection of sets which satisfies some other conditions. We can say we can find a topology there. And for that topology, this collection is nothing but the closed sets of the closed set of the topological space. That means using closed sets, we can define a topology. That is, using this theorem, we can say that the notion of closed sets are also taken as a primitive notion in topological spaces. Okay, so let us give an example here. So I take X is equal to set A comma B comma C, and I take the C is equal to, I consider a collection of subsets, C is equal to X phi singleton BC. Now look at this set which satisfies all these properties. Now here X comma phi belonging to C. Now C is closed under arbitrary. Here only arbitrary, take any arbitrary intersection. So C is closed under arbitrary intersection. Now C is closed under finite union. Okay. Now, then we can find a unique topology. What is the topology here? You just take the complement of these elements of C. So X complement, so I take phi complement, that is X, X complement, that is phi, set BC complement, that is set A. So this is a topology. And for this topology, capital C is the collection of closed. C is the closed, is the collection of all closed sets for this topological space. Okay. Okay, any doubt here? Okay. Now, using the above theorem, we can say that closed sets are also taken as the primitive notion, and we define open sets from closed set. Thus, the definition of topological space becomes, so we can define topological space also like this, say some capital X comma C, where C belonging to P of X, satisfying the properties 1 to 3. P of X means power set of X, C means family of subsets of X, which is satisfying properties 1 to 3 of the above theorem. Okay. Now we are going to define closure of a set in topological spaces. Okay, so I already said that for any topological space, suppose for any topological space X tau, any subset of the topological space generate a closed subset, and that closed subset is called its closure. The precise definition is like this. Suppose we have a topological space X comma tau, and A be a subset of X, then the closure of A with respect to the topology, that means the closure is always defined in with respect to the topology. That means if the topology varies, the closure also varies. The closure of A with respect to tau is defined as the intersection of all closed subset containing it. So that is So you write it as A closure with respect to T, that with respect to the topology tau is equal to set of all C subset of X. First of all, C is closed. Again, A is contained in C. That means we're taking the intersection. That means we find the smallest one. So that means we can say that A closure is the smallest closed set containing capital A. Okay. That means we're taking the closure of a set. We found the smallest closed set in the topological space such that A is contained in that set. Okay, now look at some examples. So let's take X is equal to set A comma B comma C, and I define tau is equal to X phi singleton A. Now if A is equal to, I take two different sets here. So here A is equal to set singleton A, and I take B is equal to set B comma C. So can you find what is A closure and B closure? Can you find what is A closure and what is B closure? What is A closure? So what are the closed sets here for this topological space? The closed sets are nothing but the complement of open set. That means the complement of members of tau. So the closed sets are here X phi and set B comma C. These are the closed sets. My question is, what is the smallest closed set containing set A? Set A contain ചെയ്യുന്ന ഏറ്റവും ചെറിയ closed sets. So I can speak Malayalam also. So what is the smallest closed set containing set A? So that is X. The only closed set containing set A is capital X. Therefore, the smallest closed set containing set A is capital X. Therefore, set A closure is equal to capital X. Okay. And what about set BC closure? Set B closure. Now we know that set BC is a closed set B comma C is a closed set. Therefore, the smallest closed set containing B is equal to set BC. Therefore, B closure is equal to set B comma C. Okay. Again, one more example. Suppose I started with real numbers R with the usual topology, and I hope that you know what is usual topology. Right, in usual topology, what are the open sets? So open sets are nothing but open intervals, their union, arbitrary union, and finite intersection. These are the open sets in usual topology. And you take capital Q, the set of all rational numbers. Then what is Q closure? You all studied the theorem. What is Q closure? The smallest closed set containing Q. So what is the smallest closed set containing Q in R with usual topology? Hello? Any problems? Hello?
No problem, no problem.
Okay. So what is the smallest? That is R itself, because we're considering Q is the smallest closed set containing Q in usual topology is R. And suppose I take R with the discrete topology. Then what is Q closure? Suppose I take R with discrete topology. Then what is Q closure? What is the smallest closed set containing Q? For a discrete topological space, we know that every set is both open and closed. That means every subsets are open, that is, which is both open and closed. Therefore, we can say that Q closure with respect to discrete topology is Q, and Q closure with respect to the usual topology is R. So that means that is why we can say that Q is dense in R with respect to usual topology, but Q is not dense in R with respect to the discrete topology. Okay. I hope. Now, for any topological space X2, so we have the following. These are the base simple results. We know that phi closure, that is the smallest closed set containing phi is phi itself. Therefore, phi closure is phi. And suppose A is closed, then A closure is equal to A. And the third one, A closure, the whole closure. This is A closure, the whole closure, which is equal to A closure. And here this means A union B, the whole closure is equal to A closure union B closure. I think everybody know the proof of these results. Okay. Now, what I'm going to rewrite the properties, that means the properties of these properties, that means the closure properties, that is phi closure is equal to phi, these properties using the terminology of operators. So that means operator means it's a function, and whose here the function whose domain is p of x and the corresponding codomain is also p of x. So I take let x to be a topological space. Define a closure operator, that means it's a function. So a function from p of x to p of x. It maps every subset here. Mu of a is mapped to its closure, a closure. Then mu satisfies. What is the first property? Phi closure is equal to phi. That means phi is a fixed point of mu. That means it maps phi to phi. That means phi is a fixed point of mu. The second property is the fixed point of mu are precisely the closed subsets of x. That is the second property here. A is closed. We know that a closure is equal to a. That means the fixed points of phi are precisely the closed subsets of x. And the third property is a closure, the whole closure is equal to a closure. That means mu is idempotent. And the third one, mu A union B, the whole closure is equal to A closure union B closure. That means mu commutes with the finite union. So now, using the terminology of operators, I define the closure. It's a closure as a function mu. It satisfies these properties. Now, using this second, that means a fixed point of mu are precisely the closed subsets of x. So we can recover. So one can recover the topology on x if one given the closure operator induced by it. That means if you know the closed sets, you take the complement, then you find the corresponding open set, and then we identify what is the topology. Now the question is, suppose we have an abstract operator theta, which is from p of x to p of x. Under what condition we can find the topology? We can find a topology on x whose closure operator coincide with theta. Okay, so the answer to this question is nothing but your axiomatic characterization of topological closure operators or Kutovsky's closure operators. So that is the following theorem. So let x be a set and theta from p of x to p of x be a function such that for all a belonging to p of x, first condition a is contained in theta of a. That means theta is an expansive operator. The second condition phi is a fixed point of theta. The third condition theta is idempotent, and fourth condition theta commutes with finite unions. Then there exists a unique topology tau on x such that theta coincide with the closure operator associated with tau, and conversely any closure operator satisfies these properties. And I think everybody knows this theorem, and this theorem is known as the axiomatic characterization of topological closure operators, and the properties 1 to 4 are known as the closure axioms in topology. So these are the preliminaries. I think everybody knows these preliminaries in your PG, and I think that everybody studied these things in your PG classes. Okay, so any doubt in this section? Okay. Now I move on to our topic. What is a closure space? And some examples of Cech-Closure spaces, etc. So, exactly what is a Cech-Closure space were introduced by Edward Cech by generalizing the notion of topological closure operator. It was introduced by Edward Cech by generalizing the notion of topological closure operator on a set X. And the definition of Cech-Closure space is given as follows. So let X be a set, and P of X denote the power set of X, a mapping. So I denote it by C. For Cech-Closure operator, I denote the mapping by small letter C. It's a function from P of X to P of X, and we call C as a Cech-Closure operator. It satisfies 3 axioms. For a topological closure operator, it satisfies 4 axioms. But for a Cech-Closure operator, it satisfies only 3 axioms. Number 1 is very similar to topological closure operator. C is idempotent. That means C phi is equal to phi. Now the second one, very similar to topological closure operator. So C is expansive. That is, C is contained in C of A for all A subset of X. Now third one is the fourth condition of topological closure operator. C of A union B is equal to, that is, C is commutes with finite union. That is, C of A union B is equal to C of A union C of B for for all A comma B subset of X. Then we say C together with the underlying set capital X is called the Cech-Closure space, and we denote it by capital X comma C. Now, so what is the difference between a Cech-Closure operator and a topological closure operator? Now, for a topological closure operator, the function is always idempotent. That means we know that a closure, the whole closure is always a closure. But whereas now we considering Cech-Closure operator, the Cech-Closure operator need not be idempotent. So that is the difference, basic difference between a topological closure operator and a Cech-Closure operator. I think the definition is easy, and everyone understood the definition of what is a Cech-Closure operator and what is the Cech-Closure space. Okay. Now, so we denote. So here we suppose I say closure space means it's a closure space, and for convenience I say what a closure space for a closure space. And suppose if C satisfies the idempotent condition, that is C of A is equal to C of A for all a subset of X, then what happens? Then C satisfies all properties of topological closure operator. In this case, we can say X comma C a topological space. That means we can say that every topological space is a closure space. Therefore, we can say that the concept of closure space is a generalization of topological spaces. I hope everybody understood what I am saying. So, a topological closure operator is always a Cech-Closure operator. Therefore, we can say that every topological space is a closure space. But the converse need not be true. The examples will be discussed later. So, this is the first concept you understood. That means every Cech-Closure operator, every topological closure operator is a Cech-Closure operator. Hence, every topological space is a Cech-Closure space. Okay. Now, for a Cech-Closure space X comma C, suppose we have a set A and A is said to be closed. So it means A is equal to C of A. That means A closure is equal, very similar to the definition of concept in topological concepts. So if A is equal to C of A, we can say that the set A is closed and a subset A of X is open provided its complement X minus A. That means its complement is closed. That is C of X minus A is equal to X minus A. Okay. Now we have a very simple theorem. Now we have a Cech-Closure space X comma C. Now I consider the collection of all open sets. That means open set means whose complement is closed. So I denote that collection by tau C. Now tau C is a topology, and tau C is called the underlying topology of the closure space X comma C. Okay. Now we prove the result. It's a very simple result, and we can prove in a very easy way. Okay. So suppose, so I consider that tau C is equal to set for A alpha, where alpha belonging to I. So that means I consider the collection of all open sets in the Cech-Closure space XC. I denote it by tau of C. Okay. So that means, so A alpha belonging to tau C means C of X minus A alpha. That means its complement is closed. That means C of X minus A alpha is equal to X minus A alpha for each alpha. Now we can prove that tau C. So what we are going is, we can prove tau C is a topology on X. So for that we can prove X comma phi belonging to tau C. Again tau C is closed under finite intersection. Again tau C is closed under arbitrary union. Okay. So clearly we can say that X comma phi belonging to tau C. Why? Because you take suppose X belonging to tau C. Why? Because take C of X minus X, which is equal to phi, that is which is equal to C of X minus X is equal to C of phi, which is equal to phi, that is same as X minus X. That means X is closed. Therefore we can say that X belonging to its complement X belonging to tau C, and similarly phi belonging to tau C. Now I take suppose A1 comma A2, say two elements of tau C. I take it as A1 comma A2 belonging to tau C. So it means that X minus A1 is equal to X minus, so C of X minus A1 is equal to X minus A1, and C of X minus A2 is equal to X minus A2. That means both that means both of complement of A1 is closed, complement of A2 is closed. And we know that X minus A1 intersection A2 is equal to X minus A1 union X minus A2. Now it takes C on both sides. Therefore, C of X minus A1 union A2 is equal to I'm sorry, this is C of not union here, this is intersection. C of x minus A1 intersection A2 is equal to, here that is C of x minus A1 using the C is commutes with finite union, therefore C of x minus A1 union C of x minus A2, and C of x minus A1 is x minus A1, again union C of x minus A2 is again x minus A2. So again x minus A1 union x minus A2 is nothing but x minus A1 intersection A2. Therefore, we get C of x minus A1 intersection A2 is equal to x minus A1 intersection A2. Therefore, x minus A1 intersection A2 is closed. Therefore, we can say that A1 intersection A2 belonging to tau C. Therefore, tau C is closed under finite intersection. Okay, now finally we can now we assume that suppose we have a collection A alpha where alpha belongs to I belonging to tau C. Then that means C of x minus A alpha is equal to x minus A alpha for each alpha. Again, you know that x minus union with respect to alpha, A alpha is equal to intersection with respect to alpha, x minus A alpha. Now we have, so we know that intersection with respect to alpha, x minus A alpha is contained in x minus A alpha for each alpha, because we are taking the intersection. This is contained in each of the set. Therefore, intersection with respect to alpha, x minus A alpha is contained in x minus A alpha for each alpha. Now take C on both sides. Therefore, we know that A subset of B, then C of A is always a subset of C of B. Now using that property, we can say that C of intersection with respect to alpha x minus A alpha is contained in a C of x minus A alpha for each alpha. Now, we know that C of x, each x minus A alpha is closed. Therefore, C of x minus A alpha is x minus A alpha. Therefore, C of intersection with respect to alpha, x minus A alpha is contained in x minus A alpha for each alpha. Now, therefore, which implies that means C of this set is contained in x minus A alpha for each alpha. Therefore, we can say that this set C of intersection with respect to alpha, x minus A alpha is contained in intersection with respect to alpha, x minus A alpha. Therefore, which implies C of intersection with respect to alpha x minus A alpha. So that means you know that C of intersection with respect to alpha, we know that intersection with respect to alpha x minus A alpha is always contained in C of intersection with respect to alpha x minus A alpha, since C is an expansive operator. Therefore, we can say that C of intersection with respect to alpha x minus A alpha is equal to intersection with respect to alpha x minus A alpha. Therefore, we get intersection with respect to alpha x minus A alpha is closed. That means this is nothing but x minus union with respect to A alpha is closed. That implies union with respect to alpha A alpha belonging to tau C. That means it satisfies all the conditions, all axioms of the topological space. Therefore, tau C is a topology on X. And this tau C is called the underlying topology of the closure space. Is it okay? Is any doubt in the proof? Kerala students, any doubt? നമ്മുടെ കുട്ടികൾക്ക് എന്തെങ്കിലും സംശയമുണ്ടോ ഞാൻ ഈ പറഞ്ഞ പ്രൂഫിൽ? ഒന്നുമില്ല, നിങ്ങൾ ബേസിക്കലി ടോപ്പോളജിക്കൽ സ്പേസിൽ ചെയ്ത അതേ കാര്യങ്ങൾ തന്നെയാണ് നിങ്ങൾ ഇവിടെയും ചെയ്യുന്നത്. ഞാൻ അതുകൊണ്ടാണ് അതിൽ ഒത്തിരി ഡീറ്റെയിൽ ആയിട്ടൊന്നും പോവാത്തത്. ഇനി എന്തെങ്കിലും പ്രശ്നങ്ങളുണ്ടെങ്കിൽ നിങ്ങൾക്ക് പറയാം. അതിൽ എവിടെയെങ്കിലും ആ ചെയ്ത ഡെഫിനിഷൻസിൽ അല്ലെങ്കിൽ ആ ചെയ്ത പ്രൂഫിൽ എന്തെങ്കിലും സംശയങ്ങളുണ്ടെങ്കിൽ ബേസിക് ചെറിയ ചെറിയ പ്രൂഫ്, ചെറിയ കാര്യങ്ങളായതുകൊണ്ടാണ് ഞാനത് പ്രൂവ് ചെയ്ത് കാണിച്ചത്. നിങ്ങൾക്ക് പെട്ടെന്ന് മനസ്സിലാവുന്ന പ്രൂഫ് ആയതുകൊണ്ടാണ്. ഓക്കെ.
Presentation is missing now. Okay. Okay.
Now we have some examples of Cech-Closure spaces. Suppose I consider let X be any set. You take any set. Now I define D. It's a function from P of X to P of X. And it is given by D of A is equal to A for all A subset of X. Now then D is a closure operator on X. Can you verify this? D is a closure operator. So how to verify D is a closure operator? So you have to check D satisfies the three axioms. That is D phi is equal to phi. Again, A subset of D of A. And the third one, A subset or equal to D of A. And the third one is D of A union B is equal to D of A union D of B. Okay, now here D phi, what is D phi here? Because it maps every set is mapped to itself. Therefore, D phi is equal to phi. Again, A subset or equal to A. Therefore, we can say that A subset of D of A. The third one, D of A union B. What is D of A union B? That is again A union B, which is same as D of A union D of B. That when D satisfies all the three axioms, therefore we can say that D is a closure operator on X. And this closure operator is called the discrete closure operator on capital X. Okay. Now my first question is D is topological? And what is the underlying topology of this closure space? Can you find this? Is D is topological? My first question. Is this closure operator is topological? What is the topological closure operator? If D is topological, D satisfies the idempotent law. That is, you take D of A. If it is same as D of A, so we can say that D is topological. Is D is topological here? What is D of A? So you take D of A. What is D of A? That is A. Again, that is D of A is equal, that is D of A is same as D of A. എല്ലാം എയിലേക്ക് തന്നെയല്ലേ മാപ്പ് ചെയ്യുന്നത്. You take D of A, that is A, and again take D of A means D of പിന്നെ നമുക്ക് D of A തന്നെ കിട്ടുന്നു. So that is again A. That is D of A is equal to A here. Therefore, we can say that D is satisfies the idempotent law also. That means D is a topological closure operator. Since D is a topological closure operator, what is the correspondent then? X D become a topological space, and what is the underlying topology of this space? What is the underlying topology? What are the closed sets here? For this closure space, what are the closed sets? ഈ closure space like closed sets ഏതൊക്കെയാണ്? What are the closed sets of this closure space? So what do you mean by closed sets in a closure space? Suppose we have a set A is closed means D of A is equal to A. And here in discrete closure space, it maps every subset. Okay, Amal Shaji. Okay, every subset is closed. Since every subset is closed, they're complement. What about the open sets here? What are the open sets here? Every subsets are again open. Then what is it? Then what is the topology? A space in a set in together with all open sets, all subsets. So what is the topology? The topology is nothing but the discrete topology. That means here, that's why this closure is known as the discrete closure operator. That means this underlying topology is nothing but the discrete topology. Okay. Now second example, again very trivial example. Let X be any set. Now I define a function I write it as I. It's a function from P of X to P of X. And it is given by I of A is equal to, for any subset A of X, A be any subset of X, I define I of A is equal to X if A not equal to phi, and is equal to phi if A equal to phi. Then you can verify that I is a closure operator. Because I phi, because you check I phi is equal to here again phi. Again, what is I of any, take any A, then what is I of A is capital X, and A is always a subset of X. Therefore, we can say that A is contained in I of A. Now again, I of A union B, A and B are non-empty, then A or any set I of A union B is equal to I of A union I of B. That means I satisfies all the three axioms. Therefore, I is a Cech-Closure operator and Xi is a closure space. And this I is called the trivial closure operator. Okay. The question is I is topological? So next question is I is topological? Yes or no? Amal Shaji, no. Why? Why I is not topological? Take I of A. Suppose there are two possibilities. Suppose A is not A. Suppose A is phi, then I of A is equal to I of A, because both are phi. And suppose A not equal to phi, then what is I of A? That is I of X. I of A is X. That is again X, which is same as I of A. Okay. Suppose there are possibilities. Suppose I take A is a non-empty set or A is an empty set. Suppose A is empty, then what is I of A? I of A is phi. Therefore, I of A is also phi. So which is same as I of A. Again, suppose if A is non-empty, ഞാൻ A non-empty ആണെന്ന് കരുതുക. ഞാൻ മലയാളം പറയുന്നത് ഞങ്ങളുടെ മലയാള കുട്ടികളോട് ഉള്ളതുകൊണ്ടാണ്. Okay, suppose A is non-empty, then what is I of A? I of A is X, therefore that is again X, which is same as I of A. That is in all cases, I of A is equal to I of A. That means I is idempotent. That means I is a topological closure operator. And what is underlying topology here? So what are the closed sets here? So what are the closed sets here? The closed sets are X and phi. The closed sets are that's only sets which maps to itself. So the sets are capital X is closed and here again capital phi is closed. So the only closed sets are capital X and capital phi. Therefore, what are the open sets here? Take the complement. Therefore, phi and X. That means a set in which the open sets are X and phi only. So what is the topology? The topology is indiscrete topology. Okay, right. So that is for indiscrete closure space, the underlying topology is nothing but the indiscrete topology. Okay. Look at the third example. Again, very simple. It's again a trivial example. So let X be a set, again, which is not finite. I don't considering it not finite set. Suppose A is a subset of X. So I define C of A is equal to phi if A is equal to phi, and which is equal to A if A is finite, and X in all other cases. So you can verify C is a closure operator. So it is easy to verify. Suppose C phi is equal to phi. Again, for A is finite, then C of A is equal to A. Therefore, A subset of C of A. In all other cases, C of A is equal to X. Therefore, again, we can say that A is contained in C of A. Therefore, C is expansive. Now you take C of A union B. Both if A and B are finite, then C of A union B is A union B, which is same as C of A union C of B. If one is finite and the other is infinite, then C of A union B is equal to capital X, which is same as C of A union C of B. That means it satisfies all the three properties. Therefore, C is a Cech-Closure operator and Xc is a Cech-Closure space. Again, the following question, the next question is C is topological and what is tau C? Can you identify? Is C is topological? നിങ്ങൾ ഫെമിലിയർ ആയിട്ടുള്ള സ്പേസ് ആണിത്. So can you identify the topology? Is C is topological? That is my first question. Is C is topological? How can you verify C is topological or not? You take C of A. There are two possibilities. Suppose A is phi, it's trivially C of phi is equal to C of phi. Suppose if A is finite, then what happens C of A? Again, that is same as C of A. And if A is not finite, then C of A is equal to C of X, which is same as C of A itself. Okay, that means in all cases, C of A is equal to C of A. Is it okay? Any doubts? That means C is topological. That is, C is idempotent, therefore C is topological. So can you identify what is the topology? Second PG is MSc students at least. So the topology is nothing but cofinite topology, very correct. The topology is cofinite topology. That means here the underlying topology is nothing but cofinite. That means here only closed sets are finite sets. So in a topological space, the only closed sets are finite set. The corresponding topology is nothing but cofinite topology. Okay. So here the topology is cofinite topology. Okay. Now these are all topological closure operators. That's why we can say that every topological space is a closure space. Now you have more examples of non-topological closure operators. So that I take X is equal to a finite set case. So I take X is equal to set to 1, 2, 3, 4. Now I define C1 is equal to C1 means set to 1. 1 means singleton set 1. So C of 1 is equal to set 1, 2. And C of 2 is equal to again set to 1, 2. And C of 3 is equal to set to 2, 3. And C of 4 is equal to set to 3, 4. That means for each singleton set, it maps to 1 maps to 1, 2, 2 maps to 1, 2, 3 maps to 2, 3, singleton set 4 maps to 3, 4. And for any other subset of X, we define C of A is equal to union union C of A where A belonging to A. That means, for example, what is C of 1, 2? That is C of 1 union C of 2. So we get set 1, 2. Okay, that is the meaning. And again, if A is equal to 5, C5 is equal to 5. Now we can verify that C is a closure operator on X. Okay, now here look at C5 is equal to again 5 here. Now we take A, any A, you know that C of A, you can verify C of A is contained, A is contained in C of A, therefore C is expansive. You take C, any two sets A and B, you take C of A union B, then clearly which is nothing but C of A union C of B. So that means here the C is satisfies all the three conditions of the Cech-Closure operator. Therefore, C is a Cech-Closure operator and hence Xc is a Cech-Closure space. My question is C is topological? Can I verify is C is topological? Try to do it. Is C is topological or not? ചെയ്യാൻ ശ്രമിച്ചു നോക്കി ടോപ്പോളജിക്കൽ ആണോ അല്ലയോ എന്ന് ശ്രമിക്കുക. So അതിനൊരു ഹിന്ദി തന്നിട്ടുണ്ട്, find C of 4. What is C of 4? That is set 3, 4. Again, I take C of 4 means C of set 3, 4. And what is C of 3, 4? That is C of 3 union C of 4. That is equal to 2, 3, 4. Which is not equal to C of 4. C of 4 is set 3, 4. That is C of 4 not equal to C of 4. Okay. Is it clear? So I take C of 4. Now C of 4 is set to 3, 4. Now C of set to 3, 4 is, for any other set, we can define C of A is union of C of A where A belonging to A. That is C of 3 union C of 4. C of 3 means that is set to 3 union set to 3, 4. Therefore, C of 4 is equal to set to 2, 3, 4. Whereas C of 4 is equal to 3, 4. They are not equal. So not equal. Therefore, we can say that C of 4 not equal to C of 4. Therefore, C is not topological. This is not a topological closure operator. So can you find what is the topology here? What are the closed sets here? So X is closed. Okay, what are the closed sets here? X is closed, phi is closed. So again, what are the another? Can you find another closed sets? Again, takes 1, 2 is a closed set here. Any other closed sets? So what are the closed sets here? So identify the closed sets. Okay, so you can do it, find the closed sets and you can find the corresponding topology. Okay, now from this example, so we can see that, so we have you can say that every topological space is a closure space, but not conversely. That means this is a closure space and this closure operator does not give a topology, does not give a topological closure, does not give a topology for that. So we can say that every topological space is a closure space, but not conversely. So one more example. So again, on N, define C from P of N to P of N. N means a set of full natural numbers. I define C from P of N to P of N, which is defined as follows. C of N is equal to set N comma N plus 1 for all. So C of N is equal to, for example, C of 1 means set to 1, 2, C of 2 means set 2, 3, etc. And for any A subset of N, we define C of A is equal to union C of A where A belonging to A if A not equal to 5 and is equal to 5 if A is equal to 5. Then we can verify that C is a closure operator. These are some questions for you. Can you check C is topological? Also identify what is the underlying topology. Okay. Here the underlying topology is nothing but the discrete indiscrete topology. You get the indiscrete topology. So from that we can say that different closure operator, that means different closure operator gives the same underlying topology. Okay. Again, now one more example. For any x comma y belonging to capital X be any set. Suppose x not equal to y, I define cxy of any set to capital A is equal to 5 if A is equal to 5, which is equal to x minus singleton y. Here x and y are any two element of capital X if A is equal to singleton set x and is equal to x otherwise. So again, this is a question for you. You can verify CXY is a closure operator on X, and these closure operators are called the infra closure operators on X. Again, the same question, check whether CXY is non-topological. Let's to prove that CXY is non-topological. Okay. Okay, next, the definition of which, what do you mean by finitely generated closure space? Suppose we have a closure space XC, and C is called finitely generated. If for any subset A of X, we can write C of A is equal to union with respect to A C of A, where A belonging to A. In this case, we can say that XC is a finitely generated closure space. We know that every finite space, that means if X is finite, then every closure space, you can prove that every closure space is finitely generated. Okay. So now, I think I have Pravas sir. Hello, Pravas sir.
Yes.
Sir, 10 തീരെ സമയം കഴിഞ്ഞോ സാറേ?
ഇല്ല, കുഴപ്പമില്ല സാർ. സാർ കുറച്ചുകൂടി കണ്ടിന്യൂ ചെയ്യും.
ഒരു 5 minutes കൂടെ, ഞാൻ 5 minute കൂടെ കണ്ടിന്യൂ ചെയ്യാം. ഓക്കെ.
നോ പ്രോബ്ലം, നോ
Now
പ്രോബ്ലം.
I define. Okay. Now I define what you mean by continuity and homeomorphisms. Like, what is the definition of continuity and homeomorphism in Cech-Closure spaces? So the before that, I define what you mean by the degree. What is the meaning of degree of a Cech-Closure operator? So let's suppose we have XC be a Cech-Closure space. If there exists a smallest natural number n, can find a smallest natural number n such that C raised to n a is equal to C raised to n plus 1 a for all a subset of X, then we can say that C is said to be of degree n, and the closure space XC is said to be of finite degree. And this is a theorem. A closure operator is topological if and only if it is of degree 1. What is the meaning of that theorem? So we know that C is topological, then C of A is equal to C of A. That means C raised to 1, A is equal to C raised to 1 plus 1. C square means C of A. That means it is idempotent. So if topological closure operator means it's an idempotent Cech-Closure operator. So a topological closure operator is of degree 1. And again, this is again and some question for you. Is every finitely generated closure operator are of finite degree? So the answer to this question is I already given an example on set of natural numbers. Now we can prove that that is finitely generated Cech-Closure operator, but it is not of finite degree. Okay. Again, I skip all this because the time is always over. Okay, again we can verify that we know that union composition of two topological closure operator need not be a closure operator. But whereas for a Cech-Closure operator, union of two Cech-Closure operator is a Cech-Closure operator, as well as composition of two Cech-Closure operator is again a Cech-Closure operator. That means C and D are closure operator on a set X. Then we can verify that C union D, it is defined as C of A union D of A for each A subset of X, and C composition D of A is equal to C of D of A for each A subset of X. Then C union D and C composition D are closure operator on X. Again, suppose C and D are two closure operator on a set X, and A is any subset of X, then we can say that C union D is contained in C composition D. For that, so here this is a short proof of that result. Suppose you know that A is always contained in D of A. That means for closure is always an expansive operator. Therefore, A is always a subset of D of A. Now, by taking C on both sides, we can see that C of A is contained in C of D of A. This is nothing but C composition D of A, and take it as equation number 1. Again, also we know that D of A is contained in, now take it this as a set. So we know that D of A is contained in C of D of A, and this is nothing but C composition D of A. Now from 1 and 2, so we can say that C composition, so C of A is contained in C composition D of A, and here we get D of A is contained in C composition D of A. From 1 and 2, we get C of A union D of A is contained in C composition D of A. So in that case, we can say that C composition D is here. C composition, here we say that C union D is contained in C composition D. Therefore, we can say that C composition D is coarser than C union D. it is not very similar to topological spaces. For a topological space, we have two topologies. Say tau1 and tau2 are two topological spaces, and we say that tau1 is coarser than tau2 means every subset of tau1 is contained in tau2. And here we can say that two closure operators, that is next definition. Suppose you have two closure operators, say C and D are two closure operator on a set X. Now I say C is weaker than D or C is coarser than D. So then D of A is contained in C of A for each A subset of X. And we denote it by C less than D if C is coarser than D. Also we can say that D is finer than C or D is stronger than C. So for an example, for any subset, for any set A, for any set X, we consider the discrete closure operator D and the indiscrete closure operator I. And we know that D of A is A for A not equal to phi, and I of A is equal to X for each A not equal to phi. Therefore, we can say that D of A is equal to A, which is contained in I of A. Therefore, we can say that I is coarser than D. Okay, so these are some basic results. Again, sorry, this is a definition of continuity in closure spaces. Suppose we have two closure spaces, say XC1 and YC2 are two closure spaces. Suppose f is a function from X to Y. Now we say that f is C continuous for Czech continuous if f of C1a is contained in C2 of f of A. If f is said to be a C homeomorphism, if f is a bijection and f of C1a is equal to C2 of f of A for every A subset of X. Very similar to topological spaces, we can prove that the composition of two continuous functions become continuous. Similarly, suppose we have xc1 to yc2 is continuous, then the corresponding topology, the underlying the function from the corresponding underlying topological space x tau c1 to y tau c2 is again continuous. But the converse of the result may not be true. Okay, I think this is the best time for finishing because I have more slides, but it is not. PRAVAS sir, I will share the PPT to the organizers. I think
Okay.
this is the best time for finishing.
Okay, sir.
Sir, ഞാൻ നിർത്തട്ടെ സാറേ, എനിക്ക് ഒത്തിരി പറയാനാണ്, ഇനി കുറെ സമയവും എടുക്കും. അത്രയും എനിക്ക് ഇത്രയും ഡീറ്റെയിൽ പോകാൻ ഒത്തിരി നേരം എടുക്കും സാറേ.
Okay, sir. You may provide some references, maybe the last slides, maybe.
Okay, fine, sir. Okay. So this is a basic text for studying Cech-Closure spaces, Edward Cech topological spaces. Again, some WJ thrown. What are the results valid in closure spaces? So these are some basic reference for studying Cech-Closure spaces. So thank you so much.